Hello everyone. Today we're gonna be discussing chapter 17. This chapter is more about the stars. In the previous chapter, in chapter 16, we have talked about the sun, and I told you like if you really understand the sun, then it would be much easier for us to discuss other stars we have in the universe. So this chapter is specifically about the stars that we have. Uh, what types of stars do we have? What sizes do they have? How are they born? How can they die? Etc. So this is what we will be discussing. And just to go briefly over this, which you already know about, you already know that different stars have different colors, and that different colors represent different surface temperatures. And something we have agreed on previously is that the blue stars are usually hotter than the red stars. And this is because the wavelength of the blue color is shorter than the wavelength of the red color, and so they have more energy, they have more temperature. And the stars in orange here are, the temperature of them is between the temperature of the hot blue stars and the temperature of the red, colder stars. Now, of course, when I say colder or cooler, it doesn't really mean that these stars are cold. They are really hot. They just have less temperature, or they are less hot than the blue stars. Akid, all stars are extremely hot, or else they wouldn't be fusing hydrogen to helium and they wouldn't be shining in our night sky. Um, One of the things also I have mentioned in the previous videos is the way of how astronomers find distances to stars. In fact, there are different ways for us to look for distances for stars. One of these methods is called the parallax method. Now, finding distances until today is still one of the most challenging things we have in astrophysics. It's not really easy to find distances. But one of the ways is called parallax, and come in, this is something we have already discussed, so I'm just gonna show you the video. A parallax is a geometric method that we use to find distances to stars by looking at the object from two different locations, from two different point of views. So for example, this is our sun and this is Earth. We all know that Earth is gonna, do this orbit around the sun once every 365 years. So uh, let's say in January, so this is January, masalan. Let's say you want to measure the distance to this red star. So in January, Earth would be here. You would be looking at the star. Okay, this is line of sight uh, to foreground star. So for this star. So anyway, January on. If I continue playing this video, of course, Earth will have to keep on moving in its orbit around the sun, and eventually it will get to this position right there. So again, you look exactly at the same star. Now, I don't want to go in details with the parallax method. I've discussed it before, but very briefly, the trigonometric method is when you look at the same object, which is the red star in this example, from two different point of views. So if you look in January, لما الأرض تكون هون, you draw a line, and then you wait 6 months, تصير الأرض هون, then you look again at the same object. Then you would have a triangle, right? You would have this triangle. Now this triangle, there are some knowns and there are some unknowns. What is unknown is the distance between Earth and the star. هيدي الأنكnown. أصلا this is what I want to find. But what is known is, first of all, the distance between Earth لما كانت بجانيوري and Earth when it became here. So it is the distance between Earth here and Earth there. So عندي هذا الخط. I also have the angles. You know, this angle, I have it. I can calculate it with the telescope, with the machine I'm using. And so if you have the angle and you have this distance, you can trigonometrically get the distance to the star. This is how we briefly do it, tangent alpha. So again, I don't want to go in details with this, but this is the trigonometric parallax method that astronomers use to find distances to stars. The problem with this method is that it only works for stars that are really close to Earth. So any star that is far away, this method will not be useful. The reason is the angle would be too small to measure. So although this method is good enough, but it's very limited for nearby stars. Anyway, so back to stars. You see, these are the terms luminosity and apparent brightness, and you should be familiar with this term, the luminosity. لأنه حكينا عنها in the previous chapter. Now, look, I want to introduce two terms here, okay? Luminosity, حبلش بالluminosity. Luminosity is the amount of energy that a star gives, that a star emits in every single second, all right? So, apparent brightness is the amount of energy we receive from the star. Okay, there's a difference here. Thing is, if you look at this example here, hold, for the image of this car. If you look at this 10 meter away, okay? If you get so close to the car, then of course you will feel that the light coming from the car is so bright. It is very bright. But if you move away 30 meters ترجع تطلع على the same light, you will realize that the light that you are receiving from that car is actually not that much, not that big, right? So this is what we call the apparent brightness. The apparent brightness depends on the distance from which you are looking at the object. أما the luminosity is the same in all of these different examples. Let me clarify this again. The sun has a specific constant luminosity. حتى in all stars in the universe, they have a specific constant luminosity. مش ضروري constant, but specific luminosity. Luminosity is the brightness of a star independently on the distance. يعني if I go to our sun and I look at the sun from a distance of 1 meter, this would be the luminosity. هذه الbrightness بتكون luminosity. But if I move away from our sun and I look at the sun from a distance of 5 light years, of course I'm not gonna see the sun as bright. I'm gonna be seeing its apparent brightness. So to wrap this up, luminosity and apparent brightness, both of them tell us about the brightness of the star. بس الفرق إنه luminosity is the real brightness of the star, as if you were standing just next to it. أما apparent brightness, it is the brightness of the star, but it depends on the distance, right? يعني لنحكي بالsolar system, the sun has one luminosity. Doesn't matter if you are living in Jupiter or Mars or Earth. The sun has a luminosity, and that is the amount of energy it's emitting in every second. أما the apparent brightness will be different from Mars to Jupiter, from Earth, if you're looking at the sun. يعني from Earth بتطلع على sun, I see it very bright. If you go further to Jupiter ترجع تطلع على sun, you will see it less bright than you were seeing it on Earth, لأنه في مسافة أكتر. So the apparent brightness change, but the luminosity is the same, right? This is why we have a relationship here, and it tells me that B, which is the apparent brightness, is equal to L, which is the real brightness of the star and the luminosity, divided by 4 pi d square, and d is the distance between the star and the observer. The more the d, كل ما كبرت the distance, the less the brightness of the star will look. Of course, it does make sense. Same example as here. أما luminosity, it doesn't change, it is constant. It is the real intrinsic property of the star. So yeah, this is about this relationship. هذا اللي كنا عم نحكيه. I also want to tell you about this term photometry. Photometry is, we have previously talked about spectroscopy, and photometry is another branch of astronomy, if you want to say. Photometry is when your job is to actually measure the brightness of stars. So you point your telescope to a star and you count the number of photons you are receiving on your telescope, and this would give you your uh, your brightness. Now إذا برجع بتطلع على هيدي equation, you see there are three unknowns. I have the B, apparent brightness, I have the L, the real brightness يلي سميناها luminosity, and I have D, the distance. If you have a telescope and you point it towards a star, your telescope will give you this term, B. Then your telescope doesn't know how far this star is. It will just give you the apparent brightness, okay? So if you have B, you still need to find L and D, right? So if you have B and then you find D with parallax, then you can find the real brightness of the star. And this is really how we do it. دايما بالequations, if you have three unknowns, like in this case B, L, and D, you need two unknowns to find the third. بهالexample in astronomy, in this chapter, we can find B, which is can be done by the telescope. You can find D by parallax until then we are able to find L, the luminosity. Okay, and it's not easy really to find the luminosity. You cannot find the real brightness of the object unless you find the apparent brightness and the distance for it. Again, apparent brightness you can find with the telescope. Distance you need to find it by parallax or other methods that we haven't really discussed. Okay. So الآن هون أعطيني example. If you want to find the luminosity of the sun and the real brightness, L is equal to B times 4 pi d square. T is distance between the sun and earth, يعني 150 million kilometers. B is the luminosity of the sun. You can find it with the telescope. بيطلع معي the real luminosity of the sun. Now there's another equation I want to explain to you, and this relationship says the following. Okay, it says that L, the luminosity again of a star, is equal to 4 pi, so constants, don't care about them. This is also a constant, I don't care about it either. So L is proportional to r squared times t to the power 4. This is the most important factor. يعني شو عم يقول لي؟ عم يقول لي إنه if r, which is the radius of the star, increases, إذا بتكبر الstar, the luminosity will increase. And it also tells me that if the surface temperature of the star increases, كمان the luminosity will increase. And this makes perfect sense, really. And also notice that the proportionality is very sensitive. يعني a small increase in R will give you a much larger increase in L. لأنه L is proportional to R square. And it is even more intense when you want to compare the relationship between L and T, because L is proportional to T to the power 4. So a very slight increase in the temperature of a star will give you much more luminosity. And this is an issue when it comes to our sun. You see, if the temperature of our sun increases by 10 degrees past, then the luminosity will increase by 10 to the power 4 degrees, a huge number. And this will cause, I think, Earth to dry up. Like Earth, I'm not sure if it can survive that amount of temperature, right? And this would be only 10 degrees increase at the surface of our sun. So yeah, كمان شغلة, if you hear of red giants, these very large luminous stars, كمان هو stars الراديوس تبعهم بيكبر, and because their radius would increase, then their luminosity will increase. So this is why they are really bright in the sky. So yeah, حكينا عن two equations so far. هاي, which you should understand, B, L, and D, and this one which you should also understand. Okay? So, next, I want to talk about the magnitude scale. What is the magnitude scale? Well, it's actually It's actually a scale that we have come up with to simplify observations. Okay. Uh, if you want to find, I'll go back a few slides لورا. I hope I have a number somewhere. Well, I don't. بس طلعوا هون luminosity. Okay. If you were to find the luminosity of the sun, it is equal to 4 pi d times b. This number, لما أحط أنا d, square it, and then b, which is the brightness, and I multiply these numbers, the number you will get is very large, it's very big. It is a big number times 10 to the power, I don't know how much, a very big number. So what we have done is we simplify our numbers and we come up with a new scale, what we call the magnitude scale. فأنا شو هعمل؟ Instead of me saying brightness, okay, instead of us using the term brightness, we're gonna be using the term apparent magnitude. Okay, it's like a new unit. كيف في عندي kilometer and meter، بدل ما أقول 1000 meter I would simply say 1 kilometer for simplicity. Same thing with apparent brightness. Apparent brightness, because it's a big number, we have invented a new term, a new scale, what we call magnitude. So apparent magnitude يعني exactly مثل apparent brightness. Okay? Just a different unit. Apparent magnitudes are usually small numbers. And similarly, kind of for the luminosity, which is the real brightness, instead of luminosity, حكينا عن we substituted with absolute magnitude. Now, I need you to focus with me on this term for a minute. لأنه luminosity مثل ما قلنا, it is the real brightness of the star. It is the brightness of the star if you were standing 1 meter away from it. So you would assume that the absolute magnitude, he command tells you about the real brightness of the star if you are moving just next to it. The only thing with absolute magnitude is that it does reflect the brightness of a star, but مش if you are standing just next to it, if you are standing 10 parsecs away from it. Okay? This is the new scale we're gonna be using. So, apparent magnitude, it is very, 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 very similar to the b, little b, the apparent brightness, which you can measure with the telescope, high with the telescope. Absolute magnitude is the brightness of a star if you were moving, if you were standing 10 parsecs away from it. This is our choice. This is what astrophysicists chose as a magnitude scale. So I need you to know them. دايما تذكروا ما تعدوا أنه magnitude is brightness. Okay, it is how much photons are escaping from that star per unit time. Okay, so شو صرنا قايلين؟ apparent brightness, luminosity, now apparent magnitude, absolute magnitude. كلهم بيحكونا عن the brightness. So let's look at an example for a magnitude scale. This is a picture of the Seven Sisters, is what is it called, or this name. It's an open cluster. It's a group of stars that were born together almost at the same time. But when you look at these stars, بتشوفوا إنه one of them is bright, another one here, this one is dim. Okay? Now, the magnitude scale بيمشي بالعكس. It is the opposite way around. So, if this star has a magnitude of plus 2.8, this one, which is dimmer, will have a magnitude of plus 8.53. Right? So, the smaller the number, the brighter the star. بيمشي بالعكس. Look at this star. It is very dim. Its magnitude is plus 7.9. Look at this star. This star is brighter than this star. So أكيد بدها يكون عندها a magnitude أقل من 7.9. Of course, you will never be asked to tell me which star has what magnitude, but you need to give me things in perspective. يعني, for example, if I tell you that the magnitude of this star is plus 3.5, if I tell you this, and then I ask you what is the magnitude of this star here, which is very dim, well, oops, sorry, So I was saying this magnitude has this star has a magnitude of plus 3.59. What is the magnitude of this star here, which is very dim? Of course, you can't tell me exactly the magnitude because you need a telescope, but you can tell me an estimate. It will be, of course, larger than 3.59. So maybe plus 8 max. This would be enough for me. What I need you to understand, though, is that magnitude scales work in the opposite direction, in the opposite way. Lish, why didn't we talk about luminosities and apparent brightness instead of magnitudes? Because if I would show you the magnitudes or the brightnesses of these stars, then you would have seen very large numbers. So again, for us not to deal with very large numbers, we have a new unit, and this is what we call the magnitude scale. This is, in this sketch, you see the magnitudes of different sky objects. Of course, the brightest object in our sky actually is the sun. So the sun has a magnitude, look, of minus 26.7. It can even be in the negative. This is how bright the sun is. The second brightest object is a full moon. It has a minus 12.6 max. The third brightest object in our night sky is Venus, the planet, minus 4.4, and so on. Naked eye, we can see up to plus 6. So everything with a magnitude of more than plus 6, we cannot see with our eyes, but we can see with telescopes. Everything with magnitudes less than plus 6, and upwards, we can see with the naked eye. Hubble Space Telescope can see objects of magnitudes up to plus 30, so very dim and very far away objects. So yeah, this is about the magnitude scale. Next, I want to talk about the color and temperatures of stars, which I think we have already discussed, so I'm just gonna skip this one. We have talked about this at the beginning of this chapter. So now it's about spectral classification. I'm not gonna talk much about this either, but I'm gonna tell you what this is all about. You see, in the night sky in the Milky Way, we have 100 billions of stars. It's true that all of them are fusing elements to other elements, and thus they are all shining, but they have different colors, and because they have different colors, then they have different temperatures. And because they have different temperatures, astronomers have decided to classify stars based on their surface temperatures. And they were like, we're gonna call the hottest stars in the universe all stars. And all stars are usually blue stars and have a surface temperature of 40,000 degrees. Lot of very, very hot. This is the surface temperature. And then B stars, we're gonna call B stars, we're gonna give this classification for stars that have surface temperature of around 30,000 degrees. If the stars are cooler than that, surface temperature of around 10,000 degrees, we're gonna call them A stars, and then F stars, and then G stars, and then K, and then M. And we also have more than that, cooler stars. What's different? The difference here is in their surface temperatures, as you can see. So this is kind of a classification that astronomers have invented to simplify things. So instead of me telling you, oh, I have just observed a yellow star, I will tell you, I have observed a G star. Then you would know that the G star is a yellow star. And by the way, our sun is a G star. It is somewhere here. And it's not so hot really compared to other stars. So imagine if our sun was an O star. Well, if our sun, which is a G star, was an O star, then yeah, life wouldn't be possible on Earth. So this is what we call spectral classification. You don't need to memorize these numbers, of course, but you need to have an idea about how this system works. Okay. Now, perhaps the most important part of this chapter is this diagram, what we call the HR diagram. Okay, now I'm gonna try to explain this diagram Uh, and if you understand this diagram and how it works, then you would have understood how stars evolve and live in their lifetime. It's very important, really, to understand this diagram. So here's the thing. If you have a telescope and you point it to 1 million stars, and for every star you find two things. First, you find the temperature, and then you find the luminosity. Okay? Luminosity, which is the real brightness. So if you have 1 million stars and you have the temperature and the luminosity of every star, what you would do as a scientist is you would draw a plot. On the x-axis you would do temperature, on the y-axis you would do luminosity, and you would scatter your points, you will plot your points. And this is exactly what has been done in this graph. And the surprise here is that when you do this, you find that stars, live in specific regions in these graphs, and they don't just scatter the graph randomly. And this is very important aspect of it. So every point here is a star. Masalan, this star has a temperature of, 2500 and the luminosity of 10 to the minus 4. This star has this temperature and that luminosity. This star has this temperature and that luminosity, and so on. Look at this group of stars. So all of this group live in the same region, and this region is what we call the main sequence region. Look at this group of stars. All of these stars live in this region, and this is what we call the giant region. Similarly here, all of these stars live in this region, and we call them the supergiants. Same here. These live here, and we call them white dwarfs. The luminosity on the y-axis, the more you go upwards, the more the luminous the star is, the more the brighter the star is as you go upward. As you go downward, the stars are getting dimmer and dimmer. So this star is really dim because it is at the lower part of the y-axis. This star is very bright. Okay? So what about the temperature? Well, the temperature works the opposite way around. So the more you go to the left, the hotter the star. The more you go to the right, the colder the star. So this star is cold. Look, temperature of 2500. The star is cold. This star, it's hot, right? This supergiant is very cold, not really cold, but it's cool and very luminous. Okay, so I hope you can make the connection. This star is, it is hot, not as hot. This one wasn't as hot as that one, but anyway, this star is hot and very bright. Okay, so you need to be familiar with this graph. Okay, so when we plot these stars, we get four different groups. This is the first group, main sequence. This is the second, giant. This is the third, supergiant. And this is white dwarf. And this is very interesting. What I'm gonna do next is I'm gonna discuss every single part by itself. Okay? The first thing I wanna discuss is the main sequence branch, which is right there. Obviously, it has most number of the stars. 90% of the stars will live in the main sequence branch. What does living in the main sequence branch means? It means that the star is fusing hydrogen to helium at its core. So all of these stars, because they live here, they are fusing hydrogen to helium at their core. Very interesting. For example, if you have a star, if you have a nebula, a cloud of gas, and then it collapses, and then suddenly the star will appear here once it starts shining. As the star lives, it's gonna be fusing hydrogen to helium at its core. And as it's doing this, it's gonna slightly climb in this region, slightly climb here. Okay, as it fuses hydrogen to helium. At some point, the star will not have any more hydrogen at its core to fuse it to helium. and it would have a lot of helium atoms at its core. And when this happens, the core will collapse because it has so much helium. So the helium core will collapse, and the radius of the star will increase. And this is when a star would jump from the main sequence to the giant branch. So stars in the giant branch were previously in the main sequence branch. When they were in the main sequence branch, they were fusing hydrogen to helium. But as the hydrogen were being used and fused to helium at the core has no more hydrogen, but it has a lot of helium. So it is more dense and it is more massive. So it collapses, the radius will increase, and thus the star will jump to the branch, to the giant branch. Should we see when it jumps to the giant branch? The temperature will drop because it's going to the right, but the luminosity will increase because it's going upwards. All stars in the giant branch are fusing helium to carbon at their core. I hope this is clear. And only 1% of the stars in night sky are actually giant stars. Then they will soon die out after that. So let's say the star is living in the giant branch for a long period of time, and then it was fusing helium to carbon, helium to carbon, helium to carbon, and then it has no more helium to fuse. What happens? The core will collapse again, but it will be the carbon core that will collapse. The star will expand so much, and in fact it will die. And this is when a giant branch star will jump and become a white dwarf. A white dwarf is a star that has died that was previously a giant star. This is really what happens, and it's very interesting because this is the evolution of stars. I'll show you some examples in a bit. Now, assume that the star but I didn't want to go here. I was just checking one thing, okay? Assume, I'll go back here. Assume that the main sequence star was here. Okay, so now we are done with the giant, forget about it. Assume you have a main sequence star here. Okay, so initially it is very large, larger than most of the main sequence stars. So if you have a star here fusing hydrogen to helium, it has no more hydrogen, it has a lot of helium at the core will collapse, the radius will increase, but it will increase so much because initially it was very massive, and it will become a supergiant, even larger than a giant star. Very interesting. And what happens in supergiant? Helium will be fused to carbon at the core. Okay, so this is really how it goes. Let me show you some some pictures for you to relate to. So I'm just showing you the comparison between a regular star and the giant star. Come on. See, this is a star, the one in white, and this is a giant star. You see how bigger they become? They move from this size to that size when they jump from the main sequence to the giant or supergiant. Maybe it's a bit exaggerated, but the sizes, but yeah, it happens. When a star becomes a giant or supergiant, and it's gonna die out soon. When a star is in a main sequence branch, and it's very healthy and still young, because it's fusing hydrogen to helium. Giant and supergiants usually fuse helium to carbon. Okay. And just to recap for white dwarfs, for white dwarfs, these are the dead stars, and I told you these are the leftovers from giant stars. So when giant stars die out, all of the gases will be ejected to space, and what will be left is the nuclear reactor, which is the white dwarf. And I'll show you a simulation. So if you want to wrap things up, this is how stars are born. This is a cloud of gas, what we call a stellar nebula. If it collapses, it will form a star. Forget about this part. Okay, forget about the lower part. If a cloud of gas, a stellar nebula, collapses, it will form an average star, like our sun. Not so big, not so small. The sun will live for 10 billion years in the main sequence branch, fusing hydrogen to helium, eventually no more hydrogen at the core. So the helium core collapses and the radius of the star increases, so it jumps to the red giant. In the red giant branch, it will be fusing helium to carbon, helium to carbon, helium to carbon, and then no more helium to fuse. The carbon core will collapse, the radius will increase, but this time it will increase so much that all of the layers of the star will be ejected to space. So you form a planetary nebula, which is a white dwarf surrounded by gases. The gases are moving in all directions, they will go away after millions of years. Eventually you are left with a white dwarf. So this is the scenario when a star is born with an average size giant branch. The second scenario would be you have a very large stellar nebula which collapsed to form a very massive star. A very massive star, much more massive than our sun. So if this is the case, you have a very hot blue star fusing hydrogen to helium, very similar to the first scenario, but when it has no more hydrogen to fuse, the helium core will collapse and the star will expand and it will become a supergiant, even larger than giants. When it becomes a supergiant, it is fusing helium to carbon, no more helium to fuse. The carbon core will collapse in this case, but it will not form a nebula. When the carbon core collapses, when the carbon cores collapse for red giants, red supergiants, the core will collapse so much on itself that it will explode. And when it explodes, it does what we call the supernova explosion. And when you have a supernova explosion, you will either create something that we call a neutron star, or it will create a black hole. So this is what really happens in the life cycle of a star. Very interesting and very cyclic and completely recyclable. Because all of these gases, for example, that were ejected will be later used to form a nebula to form more stars. So I hope you can relate what we have discussed here with the HR diagram, because if you do, then I promise this would be what you need to know to understand all about the stars. Now let me show you this picture, for example. Look, hey, this here is a white dwarf. These gases were all contained around that white dwarf when the star was alive. See, this is a nebula. This is the stage here, planetary nebula. So before it became like I showed you, it was a red giant. So imagine this as a red giant. So you have to rewind all of these gases and put them around that star. Very interesting. Look how a star, this simulation shows you how a star, like our sun actually, this what will happen to our sun. When it moves from the main sequence to the giant branch, this is what happens. We have agreed, when there's no more hydrogen at the core will collapse, the helium core will collapse, and the star will expand, and it become a giant star. And look at it now. So this is our sun. Now it's getting larger and larger and larger. It's a giant star now. And after it's a giant star, what happens? It's gonna pulsate. It will throw all of the gases away, and it will become a planetary nebula. See? Nebula. It's forming the planetary nebula now. All of the gases will be able to escape, and then you will be left with the nuclear reactor, the core of that star. Yeah, so this is the story of how they become like they are. Another scenario, Tafana, we have agreed that if the star is so large, it will not only become a giant, it will become a supergiant, and then it will do a supernova explosion like you see in the simulation. Some stars, if they are so large, they will explode and they will give you so much light. You know, one star, one supernova explosion is brighter than an entire galaxy. So this is the most energetic explosion we have in the universe, the supernova. And remember, these are the explosions that form either neutron stars or black holes. Well, I want to show you this also. I haven't discussed it before. You know, some weird things happen sometimes in the universe. Look, this is a white dwarf, yani a star that has died. And this is a main sequence star, a living young star. Sometimes if a white dwarf come closer to a main sequence star like this one, like our sun, what the white dwarf will do, it will steal the gases from the larger star and it will live again, leaving the previously alive star dead in the end. So this white dwarf, which is a dead star, will come next to that larger star. It will see the gases and it will live again. See how the white dwarf is stealing those gases from the larger star? This is what we call type 1 supernova. Don't worry about it much, but it's just interesting to share. See, now it started to fuse. It has seen enough gases to start the fusion reaction. Oh yeah, and one more thing I want to tell you about is something we call brown dwarfs. Now, brown dwarfs are really the unborn stars of the universe, if you want to say. You cannot find them on the HR diagram because they are really cold. You will find them somewhere at they are cold with low luminosity. But what I want to tell you is sometimes when you have a cloud of gas, when it collapses, it doesn't have enough temperature or density or pressure to fuse hydrogen to helium. So what you would be left with is a sphere of gas that wanted to become a star but couldn't fuse and couldn't shine, so we call it a brown dwarf. This is an image of a brown dwarf, artistic one, because you can't see them directly. This is a brown dwarf. If if it had enough gases, it would have became a star. But look, it's not a star, it's not a planet, it's somewhere in between. Brown dwarfs. You can read a bit about them. So yeah, this is all I wanted to say about the nature of the stars and the evolution of the stars. I mean, there's a lot more info we can talk about and discuss, but I think this is a brief overview about the nature of the stars and how they live and evolve and survive. Thank you for watching.